Oh, it worked quickly.
Hello, Tommaso.
Oh, hello, Anton. How are you? Good to see you.
Good question.
So I guess the seminar is 1 hour, all included, right? All inclusive. And I guess you can stop me whenever you want.
It's usually a bit longer. I mean, it's 1 hour, but because participants often ask questions, it can, depending on questions, maybe 1.5 hours.
Okay. Are you in Australia, Alexander?
No.
I see the Bondi.
Oh, yeah, but it's
logo.
I will hopefully come there actually next in 2 weeks.
Okay. So you tell me when to start, right, Alexander?
Yeah, it's already 2 in our time, so maybe we can wait a few minutes.
Sure. Yes.
Okay. Well, Alexander is asking me to introduce you to Tommaso, and I'll be very glad to do so. Well, it's a pleasure and honor, yeah, definitely a very big pleasure for me to see Tommaso, because I haven't seen him for a while, and we know each other from way back. Tommaso is a very well-known econometrician. He's done a lot of very exciting work, very interesting stuff. He's a editor in some editorial positions in a number of universities. So we're very happy to have him here today, Tommaso. So as Alex said, it's assuming you can still see and hear me, it's about an hour, and we if it's okay, we interrupt people politely. So is that all right if we interrupt? Do you want questions at the end?
Yes, of course. No, feel free to interrupt me anytime.
All right. Well, then I just want to make sure that people can see everything and hear everything, which I think is the case. So just take it away, Tommaso. Great to have you.
Thank you very much, Artem. Thank you for this nice introduction, and a warm thank also to CEBA for inviting me, and it's a great pleasure to be here. So I will start sharing my slides. Okay, so as you see, the title of my talk is another look at dependence, the most predictable aspect of time series. And so this is about dependence and predictability in univariate time series. So, this is a very long story. As you know, the idea of measuring dependence has a long tradition in statistics, econometrics, and time series analysis. We all know and we all use traditional measures such as the Bravais-Pearson autocorrelation function, and we are all aware of its limitations. So for instance, the plot of the sample autocorrelation function of a time series and the sample partial autocorrelation function are traditional identification tools we know very well, and they belong to our everyday kit. We know also about the limitations of this measure of association of serial dependence. It only measures linear association, and it's when it's close to zero, it doesn't imply that the stochastic process underlying the time series is not predictable. Some other measures have different properties, such as the Spearman's rank correlation coefficient and Kendall's tau, and they measure monotonic association. So they have several virtues vis-a-vis the Bravais-Pearson correlation coefficient. Now, moving away from these traditional measures, alternative measures are being developed, and there is, as I said, a very wide and deep literature on this topic. So the interest has been lying in providing less restrictive measure of serial dependence that may have a bearing on the predictability, that can tell you something about the predictability of a process. Just to quote a few of these measures, Hong proposed a measure of dependence based on the covariance between the characteristic function of xt and the lag xt minus k. Then Zhu has extended the notion of distance covariance and correlation to the class of strictly stationary time series processes. Phocianos and Pistilus, based on the idea of the auto-distance covariance function, have proposed this test of serial independence, which they also extended to the multivariate framework. Now, these measures are quite ambitious. Essentially, they aim at capturing possible form of nonlinear serial dependence. Also, there is a tradition in testing for conditional mean independence. That is this contribution by Escanziano and Velasco proposed tests of conditional mean dependence based on the covariance between xt and the characteristic function of the lag xt minus k. And Shao and Zhang have elaborated on that, proposing measure of the degree of conditional mean independence of xt from its past, which has also been extended to the multivariate framework. There are also other contributions dealing with the Gini autocovariance function, which measures the degree of monotonicity of the relationship between xt and its lags. Okay, so this paper is a bit motivated by this literature. And one of the key questions that are asked is whether we reject independence or conditional mean independence. Well, you know, when you apply this test to economic and financial time series, the answer is we don't fail to reject independence or conditional mean independence. So typically, we do have some form of possibly nonlinear serial dependence in time series, which we can discover by applying this test. But after we have decided that that we fail to reject independence, the next issue is why do we reject independence? And so I've been looking into this problem in a sense. So the main motivation of this paper is to provide answer to both questions, not only to reject serial independence, but also to assess why. So what is the predictable aspect of a time series that we can discover? My focus will be on the mutual information, which is a measure of dependence defined as the Kullback-Leibler divergence between the joint probability density function and the product of the marginal densities. It has a long tradition in time series. I have here some references by Ibragimov and Rozanov, Jewell and Bloomfield, and other contributions have been using this measure as a measure of dependence. It has a tradition in information and communication theory and also in data science. Here is a list of some recent contributions. Now, more specifically, in the analysis of time series, this measure, which is the mutual information as between two random variables, a random variable and its lagged version, has been used by Granger and Lin in a very popular contribution. And my approach is to use this measure with in a spirit that is similar to this publication by Goriro and Jasiek, who proposed a nonlinear autocorrelogram. And there is also a contribution in an unpublished paper by Owen, who looks at the optimal transformation of an autoregressive process by adapting the alternating conditional expectation algorithm by Bremen and Friedman. So it's very close to these two approaches. To summarize what I do, I consider the mutual information between past and future as my target measure of predictability. This is a broad measure of predictability that takes into account predictability at possibly all future forecast horizons rather than focusing on predictability one step ahead. Now, the most predictable aspect of the time series would be defined as that measurable transformation for which the mutual information between past and future is maximized. And this transformation arises from combining linearly the elements of a basis. And I will provide a discussion of the options available, what kind of basis function can we use, what are the merits of each individual strategy. So the mutual information is then must be estimated along with the parameters that characterize the transformation of our stochastic process. And so I will discuss also inference, how do we estimate the most predictable aspect or aspects of the time series. If this is okay, Tommaso, yes.
Can I ask a few things? So this,
yes.
So clearly you mentioned that this is a nonlinear dependence, which makes you think about copulus, and there's the Fan paper that applies copulus to model dependence in time series that you haven't mentioned, but I wonder. So this is going to be in. So you mentioned it's a quantiles of the distribution of the past axis and the future axis, right? So there is a built-in copula structure there because it's quantiles, right? So I wonder why there's no, I mean, why you choose not to go that route, because this, what you're showing on the slide now would also be a function of the dependent structure, right?
Yes, of course. Yes, of course. And I'll mention copulas later on. Okay. So yes, it wasn't not in my review. Of course, there is a long tradition in using copulae for dependence in time series. And of course, yes, you're perfectly right.
Also,
I'll bring up copulas later on. Yes.
One other thing that there's also the tradition about is, of course, and you mentioned Shekeli, and there is I've used this results in the paper that when there's a tradition in a statistic that I'm sure you know about fairly generic results about how to take uncorrelated random variables, transform them, and produce dependence of specific nature. Right, and I think Mori and Shekeli is one. You might have seen. So yeah, so I mean that's clearly should be related to what you do as well. Mori and Shekeli is something like 2007.
Thank you very much for the reference, Artem.
Yeah, sure.
Right, so I would like to have a brief introduction about the mutual information, and later see how this relates to the problem at hand. So let us consider x and y as two vectors of continuous random variables with joint PDF fx and y, and marginal density in fx and fy. The mutual information between these two random vectors is defined as the Kullback-Leibler divergence between the joint and the product of the marginals, and that's this is how it is defined. As a measure of dependence, it has several nice properties. It is non-negative, first of all. It is zero if and only if x and y are independent. It is symmetric with respect to x and y. It is invariant to one-to-one transformation of x and y. And it's related to entropy in this way. So it's the marginal entropy minus the conditional entropy, or equivalently, you could see as the sum of the entropies of the two individual variables minus the joint entropy. We will use also a transformation of this measure, which is the mutual information index, which is in the range 0, 1. That's the transformation for that. And we define the partial mutual information between x and y given another vector of random variable z as this Kullback-Leibler divergence, where everything now is conditional on z. Okay, so that's the definition, the target measure of, say, serial dependence and predictability that I'm considering. I would like to briefly introduce some notation and state what I'm considering. So I will be considering a process which is stationary, strictly stationary and ergodic around some zero mean. And I will assume that there exists an autocovariance function, which is finite. So I will denote by gamma k the autocovariance function of a collection of k random variables. By rho k, I will denote the autocorrelation function. And I will need also the concept of a partial autocorrelation function, which is essentially arising from this problem of optimal linear prediction. Suppose we want to predict xt based on k past values, and that then the coefficient of this projection, phi kk, is a number between -1 and 1, which represents the partial autocorrelation between xt and xt minus k. It can be computed recursively via an efficient algorithm, which is the Darbin-Levinson algorithm. Now, for Gaussian processes, the interpretation of all these things is somehow simplified. So phi kk now it's a conditional correlation. Then the mutual information between xt and a future value xt plus k is a transformation of the square correlation coefficient, rho k. So this is the expression for the mutual information between these two random variables. And the mutual information index would be just the square of the autocorrelation function at like k. Now, the partial mutual information between the same two variables, conditional on the intermediate random variables, would be simply a function of the kth partial autocorrelation. So it's this simple function of the square of the partial autocorrelation coefficient, which is computed efficiently by the Darbin-Levinson algorithm. So this is just a review of the notation. This is a review of the Darbin-Levinson algorithm, but I think that given that the audience is very well knowledgeable about these facts, we can skip this review. Now, as I said, I will be looking at the mutual information between past and future as my target measure of predictability. And I will define the most predictable aspect of the time series as that particular transformation of the original time series for which the information between past and future is as large as possible. That's my definition. So let's start with this result, which holds in general for strictly stationary random processes. Let's denote by pi k the partial mutual information between the random variables xt and xt plus k, given all the intermediate random variables, right? We denote it by pi k. Now, the mutual information between n, a collection of n past values, and m future values, right, of future random variables, admits the following nice decomposition. Is the cumulative sum of all the partial information conditional on the between each variable in the past with each variable in the future, given all the intermediate variables, both past and future. So that's one result that can be proved easily by the property of the mutual information and its decomposition. Notice here that there is this connection with copula, because essentially pi k, which is the key ingredient here, the partial mutual information, is the expected log copula between the distribution of xt and xt minus k, conditional on the intermediate random variables. So despite the notation, that's the basic fact. That's the basic fact. Right, so now let us consider the indefinite past. Suppose that we are at time n and we consider the collection of random variables up to and including time n, and we consider the future up to time n plus h. So let's xfh denote, xfh is the future starting from time n plus h to infinity, right? So there is a gap of h time units between the past and the future here. Okay, when h is equal to 1 and we consider the immediate future after time n, then we denote this collection of random variables as xf simply. Right? So now we are interested in the mutual information between the complete past and the indefinite future of a time series. And this mutual information between the past and the future is just the cumulative sum of all the partial mutual information pi k's. So that's the formula which, in a sense, generalizes what Ibragimov and Rozanov do for the class of Gaussian processes. So that's what we would like to get to, and that's the measure of predictability that we target, which is quite ambitious because this involves the summation of infinite partial mutual information indices.
But Tommaso, hold on.
Yes.
K is the horizon.
Yes, K is essentially is the time distance between xt and xt plus K.
Okay, I see. I see. Because on that formula, you have K on the right-hand side. Yeah, so K.
Oh, right. Yes, I don't anymore have a K. You mean, so here I don't have K anymore. So I collect the indefinite collection of the past and the future.
Right. Okay, got it.
So I think that, yes. Okay, so later on, we will assume that this quantity is finite, which this assumption as a name, we assume that the process is absolutely regular. So this is a finite quantity. And that this process is absolutely regular implies that the process is also information regular, which means that if you take a collection of future values which has a time distance of h, so you have a gap of h random variables in between, then this mutual information gets towards 0. Now, absolute regularity is a form of which is somewhat more strict than strong mixing, but that's the idea. The serial dependence of a process is so the serial dependence is going to 0 so rapidly that this is finite. That's the idea. Now, for Gaussian processes, this simplifies quite considerably because now the partial mutual information is a function of the partial autocorrelation. So if xt is a Gaussian process, then the mutual information between past and future is this sum of all the logs of 1 minus phi kk squared. Phi kk is the partial autocorrelation at lag k between the random variables. Some illustrations: if you have a Gaussian AR1 process, then the mutual information between past and future is simply this expression, depending only on the autoregressive coefficient phi on its square. And the mutual information index between 0 and 1 would be the square of the autoregressive coefficient. Similar things hold for the log normal stochastic volatility model, where again, the mutual information depends on the square of the coefficient of the autoregressive coefficient of the log volatility. Now, there are processes with infinite mutual information that we don't consider here. And any process which is fractionally differenced, like here, so any fractional noise process or some non-invertible process with a fractional d less than 1/2, the mutual information for this process would be infinite, would be diverging, right? And so we don't consider these processes. The Gaussian AR1 process is not a Gaussian process. It's not a Gaussian process and tells you about what are the difficulties in getting closed form expression for the mutual information, even in simple case when we know and we specify the model in terms of the conditional distribution only. Okay, so that's the story so far. We consider the mutual information as the target predictability measure. This has say complicated form in the general case, depending on the partial mutual information, which is a complicated object, say. Things simplify considerably if we consider Gaussian processes, of course, where everything now is available in closed form. Okay, now let's get towards the main idea. So let us define the most predictable aspect of the time series with this background in mind. So let us consider a set of measurable functions of xt, here defined, so that in a sense, this collection of functions of xt is non-singular. if we denote by ht the vector collecting these functions, then we assume that this function has a autocovariance or cross-covariance function, which is non-singular, meaning that gamma h0 is positive definite, and this we assume that each one carries information of its own. Right, so I will later say what kind of basis function do we choose for this collection of functions. So suppose that we have R features that are obtained from xt, and these features are non-singular. Then I will collect these features by a linear combination of this feature with unknown coefficients in a vector beta. This vector has R elements, and I will consider a transformation of this set of basis functions, a linear transformation, such that the variance of this linear transformation is 1. So I have a normalization constraint, and I consider ZT star or a monotonic transformation thereof, so that I maximize the mutual information of ZT. Now here, so let me review what is the story here. We defined a set of basis function, R of those, then we combine them linearly into a ZT star under this constraint. And then, you know, we may have a transformation, a monotonic transformation, which could be the identity transformation, or it could be a normalizing transform. Then we define the most predictable aspect of xt as that contemporaneous transformation, which is a G transformation of this linear combination, such that the mutual information between the past and the future of ZT is a maximum, right? So ZP here denotes the past, and ZF denotes the future of this derived random variable. And of course, we may define the second best predictable aspect of xt as that orthogonal aspect to the first, or with some orthogonality constraint, which maximizes again the mutual information. So this WT would be defined as a monotonic transformation. Think of the identity transformation of a linear combination of the basis function with coefficient theta j that are orthogonal to the vector beta in the metric of gamma h0, and subject to a normalization constraint again. And the vector theta is chosen so as to maximize the mutual information between past and future with respect to WT now.
Tommaso.
Yes.
So what is the optimization over here?
Over beta, right? So my unknown is beta.
I see.
H is a measurable function. So this is known.
Okay, so H is unknown, R is known?
Yes, so R is a matter of inference, of course. R is a matter of inference, and suppose for the moment that is fixed, right, that we've chosen R. So the problem would be estimating beta. That's the main problem. Yeah. Another problem is, of course, the mutual information is a function of infinite terms. We would need some semi-parametric or non-parametric estimates, so that we would need to truncate an infinite sum. So we would have also a bandwidth parameter to estimate. As I will.
So it's basically like it's a non-parametric estimation of
yes,
information using so using basis functions. Yeah, okay. Thanks.
Yes. Okay, so what do we choose for the functions ht? So ht can be thought as a feature vector, so the problem could be context specific, right? We have some freedom in choosing ht depending on the problem. However, what I do, I concentrate on a couple of choices that can be, say, can have some generality. So I will propose a couple of set of basis functions that are evaluated at location shifts of the original process. Namely, I will consider xt minus a quantile, which is the alpha jth quantile of the distribution of the marginal distribution of xt. So q of alpha j will be the jth quantile corresponding to some probability level alpha j in 0, 1. Now, a possible choice is the set of hinge basis function located at the quantiles qj, which is q of alpha j, where alpha j is chosen in this way. So think, for instance, if r star is equal to 1, then you pick up the median. If r star is equal to 2, then you take the first 1/3 of the distribution and the second third of the distribution. If r and so on and so forth. If r is equal to 3, you take the quartiles and so on. So this set of basis function come as a pair, and this is the description of this pair, and the graph is given here. You see, for each quantile that you have to consider, you consider a function like this. This is the first in red, and the second would be the one in dashed blue here, right? So this is a description of two basis function, of a pair of basis function making up the hinge basis. And you have r star of those functions located at the quantiles of the distribution that you have chosen. Another possibility is to use a logistic basis. So you can define the hj functions to be the logistic transformation of xt minus the location shift of xt scaled by some quantity tau, which again is a matter of inference. But you see, this could be decided on the basis of the characteristic of the distribution. And again, this function would be located at the quantiles. So for instance, here I have 4 functions located at the quintiles of the distribution. So you see 4 functions located at the quintiles of the distribution of x. So these are 2 possible choices, and I will use them most. Of course, you could use a natural cubic spline basis with natural boundary constraints. There are other choices of basis function that can be used. For instance, I've been experimenting a little bit with a set of derivatives of the check function that you use for the quantilogram in the paper by Linton and Wang, for instance. So you have many interesting possibilities here. And of course, you know, the choice of the basis function can be made so that you don't have to assume much of the of xt. So for instance, you can give up the assumption that there exists a second moment, for instance, by a suitable choice of this basis function. And also, you know, if you allow R to depend on T, then your problem of estimating the optimal transformation has a long tradition again in statistics, and it's a particular instance of the method of sim extremum estimation. And here is the reference. Chen and Shen is one possible reference for this literature. Although you see in my example, my choice of R will be, you know, typically very small. I will be happy with a very small value of R. Now, statistical inference. So how do we estimate from a time series the optimal transformation and the second best optimal transformation and so on and so forth? Now, actually, this is something I'm developing at the moment. I mean, I have to still look at the asymptotic properties of my proposal. I'm very optimistic about it. And let me tell you what I will be doing. Of course, the location of my basis function will be at the empirical quantiles of the distribution of xt of my time series. Then I will denote by ht my set of basis function evaluated at the time series values. You will use the same notation. And H bar will be the mean, and the autocovariance matrix will be gamma HK. This is the variance covariance of the functions in HT. Now, the vector beta, which is my unknown vector, will be estimated by maximizing the mutual information here. This is my objective function, which now depends also on a bandwidth parameter L. And the bandwidth parameter regulates the truncation of my partial autocorrelation. So I will estimate my mutual information by a truncated cumulative sum of the partial autocorrelation, which depend on beta, right? And the coefficient will be obtained by a regularized Darby-Levinson estimator, which I have been recently proposing in a paper with my colleague Alessandro Giovanelli. So essentially, I will have a weighting function applied to the sample partial autocorrelation, which regularizes the rate at which they go to zero, and after a while, I truncate this sum. I will explain it in a second. Then you see, for the time being, R is fixed. The number of elements in the basis is fixed, and I will say something later on about the selection of R. Okay, now for a given beta,
Tommaso.
yes.
Maybe you could mention a little bit about the application of this.
Yes, of course.
So
I will
once you have the this object identified and estimated, then you would be doing something with this, because this object per se, I'm not sure what is the interest of the.
Yes. So very good question. So that's
I'm asking here because you can do, of course, statistical inference on this object, but it would be good also to have in mind what is the final goal, so that to think in parallel how statistical inference translates to the final object of interest. I don't know, maybe you want to forecast, I don't know, stock returns or macro variable, or because statistical inference at the end, which will be reported, is not this, what is on this slides, but on something what applied people want to see. That's why I'm asking it here.
Yes, you're quite right. And in fact, you know, in my conclusion, I will point at that. That's one of the potential uses. But you see, already from the application, we learn a lot. So for instance, we can learn about some asymmetries existing in the distribution and the serial dependence structure of a process by looking at the betas, comparing the betas. They are defined at symmetric quantiles in a sense. So potential asymmetries, some testing can be going on. And I agree with you. What I do so far is a bit descriptive. I want to look at and find out what is the best predictable aspect of a time series. And for instance, for financial time series, the discovery is that volatility is the most predictable aspect. So what is the discovery? We all know that volatility is the thing that drives the serial dependence, after all, of this object. But you see, already with this, we can do something. So Igor, just wait and see. So perhaps I will speed up a little bit on these bits. And now, it is crucial, L is a parameter. It's a bit of a nuisance parameter that you need to truncate this infinite sum. How do we determine that? Essentially, we regularize the partial autocorrelation, the sample partial autocorrelation of the Z of the transform variable, which depends on beta every time, according to weighting function, which is a trapezoidal kernel. So in practice, we retain a number L of partial autocorrelation, of sample partial autocorrelation, then we taper off to zero the remaining ones up to twice L. And the choice of the bandwidth can be done by criteria such as, you know, the one that is proposed here. So essentially, you conduct an approximate 95% simultaneous test that the next number of partial autocorrelation at 0 jointly, right? It's like a rule for selecting L. So we have rules for selecting L. So we have also information criteria for selecting L. They seem to work pretty well. Maximization in practice is carried out by a numerical optimization routine, handling on linear equality constraints such as fmin-con in MATLAB, and things run smoothly and efficiently because the problem and the function is well behaved. Now, it's very important to provide good initial values because of the availability of multiple maxima of the criterion function. And a key idea here is to start and initialize the value according to the eigenvector scaled by the corresponding eigenvalue, which maximizes the mutual information. That's usually a very excellent starting point. I will illustrate it in a second. Now, for the selection of R, a criterion based on the mutual information borrowed from the literature, in particular in a paper by Li and Xie, which penalizes, this is an extension of their criterion. Their criterion is built for selecting autoregressive processes. Now we extend this criterion by penalizing also for the number of basis function that we use, and that seems to work well. Okay, some illustrations. The first one is rather trivial, right? Not very useful, I would say. But you see, consider the log normal first order autoregressive process with coefficient 0.5, right? We know that if we take log, then it's a Gaussian process, and the mutual correlation depends on the square of 0.5. And in fact, we know the true mutual information which 0.1438, right? So we evaluate the ability to recover this value by a Monte Carlo exercise, and I use in my illustration 3 functions located at the quartiles, and the functions are inch basis functions. So here is a simulated series from this experiment. That's the sample ACF. When you derive the most predictable aspect of this time series, this is what you get for this time series, and that's the ACF of the transformed time series. As you can see, the optimal transformation is the log transformation in practice, and we do also see that as t increases, there is the convergence of the distribution of the mutual information estimated to the true value, which here is in black. The black is the true value, and the green is the distribution for 5,000 observation, and so on and so forth. So very trivial exercise. Now, the second illustration deals with this process. This process is a nonlinear moving average process, and is referenced in this literature about dependence. So, for instance, in the auto distance covariance application, Fokianos and Pistillu investigated this process and the ability to find out serial dependency in this process. Now, this process is serially uncorrelated. So the sample ACF of xt is centered around 0, but it's not independent. In fact, you know, if you take the absolute value of the squares, you will find that this is a positively autocorrelated processes at lag 1 and 2. Okay, I generate a sample realization of 1,000 observation. Here it is, right? And you could see the sample ACF in red, right? We don't see much. We don't see much, right? All the autocorrelations are very low, close to 0 for this red time series. Now, I work out the most predictable aspect using 2 hinge basis function located at the median. And this is my optimal transformation, right? My optimal transformation that I normalize later on. And You see, I also find that the second best predictable aspect of the time series is just white noise. So the optimal transformation looks like this. If I plot ZT versus XT, I get this optimal transformation. And this is the plot of the transform time series. And now the two large autocorrelation lag 1 and lag 2 show up. My third illustration deals with the US. Yes.
May I ask a question? It's
yes.
It's related to autoregressive processes and moving average processes. So autoregressive processes are naturally Markov processes, and Markov processes are generated, completely characterized by copulas for subsequent observations, right? XT minus 1 XT. And similar representation, copula characterizations also hold for Markov processes of higher order, like moving average process of order 2 is second order Markov process. Can the results on the relationship between dependence measures, you mentioned those for Gaussian autoregressive processes with implications for estimation, and also the results like for moving average processes be extended to the general case of Markov processes and higher order Markov processes?
So, sorry, Rustam, could you repeat your question?
The results that you had for autoregressive processes, the Markov processes of order 1, those are characterized by bivariate copulas.
Yes.
For subsequent observations, XT minus 1 XT, and moving average processes of order 2 are Markov processes of order 2.
Yes.
Those can be characterized by bivariate and trivariate copulas completely. I was wondering if the results for autoregressive processes and moving average processes that you presented, including relationships between dependence measures, be extended to the case of Markov processes and higher order Markov processes.
Oh, I see. So you mean this decomposition here?
There was a relationship
in terms of partial information
between mutual information and phi-square measure in particular, right?
Oh, yes, yes, and the phi-square measure, yes.
With implications for estimation.
Yes.
And also, these results for moving average processes of order 2, if they are analogs, getting their analogs in the case of Markov processes of order 2 would be interesting. In terms of different copulas that generate Markov.
Yes, yes. So, well, for Gaussian processes, it would hold anyway, that this thing become very easy and a function of all the partial autocorrelation sequence squared. For nonlinear moving average process, then this I have to investigate it, but again, this would be non-zero for all lags, and you have several dependencies that would show up. But I don't have an answer, direct answer for your question, Rustam.
Yeah, thank you. We had papers on new statistics characterizations for couples of dependent variables with implications for characterizations of higher order Markov processes that give represent relationships between different dependence measures. Maybe that would be of interest. I will put it.
Yes.
Thank you.
Yes, thank you very much. Yes. Okay, let's go back to the illustrations. This particular illustration deals with the US index of industrial production. I actually consider the monthly growth of industrial production. This is the time series that I'm observing, right? And of course, it's heavily affected by the COVID-19 pandemics, right? So you have a big drop in production. Subsequently, you have very large increases, very high monthly growth rates. And for this particular case, I selected a logistic basis with R equal to 3. And what happens here is, to cut the story short, is that my optimal transformation is a robust transformation of the original time series, essentially cutting down the influence that this point exerts on the autocorrelation pattern. So the optimal transformation that I estimate is this logistic shape, in a sense, this sigmoid shape, and of course reduces the impact and can be seen as a data-driven robust transformation of the data. That would be my transform time series. Now we see that the autocorrelation pattern and the serial dependence now it's much richer than before. So the red would be the autocorrelation sequence associated to this time series. The blue would be associated to the optimal transformation. Now, interestingly, if you look at the second most predictable aspect of the time series, you discover that volatility is there. So the second most predictable aspect is the volatility of the time series. My final illustration deals with the Standard & Poor's index returns, this time series in particular, right? That's my original time series. That's the sample ACF for the series. Now, I select a hinge basis function considering only r equal to 1. Sorry, this is an r star. So I consider essentially exactly this situation. This situation here where these two functions are located at the median. That's enough, right? Every other, so using a larger R would lead to some overfitting in a sense. So what happens here? So I have these two basis functions. This is their sample covariance matrix. This is the variance covariance matrix. So these two functions are negatively correlated. I have one eigenvector which essentially is associated to the largest eigenvalue, which essentially sits around here, right? Around here. So this is the space of the solutions. So this is the set of points in the satisfying the constraints. And this is the space of beta 1 and beta 2. In this case, it's nice to plot it. This is the behavior of the mutual information for L equal to 10, which is the value that I select. And there is a maximum here, which is very close to the second eigenvector scaled by the square root of the eigenvalue, which essentially points out at a transformation, which is the volatility of the process. So this is the optimal transformation of the process, and this is plotted here. This is the serial correlation pattern of my optimal transformation. And when you normalize this transform, you get something like log volatility in a sense, right? This is log volatility. The second, sorry, yes.
Sorry, I was just coughing. I'm a bit sick.
Oh,
but
right.
Tommaso, since you made since you paused, let me ask you this. So yes. I'm sorry to interrupt this application, but what is the point of doing the modeling of the the modeling of the transformation, the modeling of mutual information through the transformation of the initial X, as opposed to modeling the ranks of the initial X. So if remember there's this representation results that so you can take anything that's possibly uncorrelated, right? And any multivariate distribution would be obtainable as a transformation of those X's. So it seems to me that H is very important, right? So
yes. So H is important. As I said, it's a bit context specific, although you get similar result here if you use a logistic basis or a hinge basis function. And you see the rank transformation would be useful here, right? In this situation where things are monotonic, you need to reduce the impact of these guys. So rank transformation here is what it is, essentially. But not much in these situations where the transformation is like this. So when you have the volatility, then you don't have a monotonic transformation that you're looking at. Like think of the square, the absolute value. And this is somewhat more general because it can capture asymmetries in this transformation, right? Like, you know, one side goes, you see, for instance, the asymmetry here is that this coefficient is larger than that, right? And the idea would be, is this different from that significantly, right? So that's the next idea. So that I capture some asymmetry in the volatility process, which can be due to leverage, or it can be due to having some disturbance here, which is inherently skewed, right? Some
you know, I see that, but why not model the copula directly?
Right. Why not module the copula? Well, that's of course that's a perfect valid approach, and it's an alternative approach. Here you see, I could see this aspect. I could use it, for instance, so coming back to the Igor's question, so perhaps I can say something. This is not invertible as a transformation, right? But I could say something about, say, the left tail or the right tail when volatility is very high here. So when volatility is very high, I could say something, of course, either for positive or negative return. So that would be the next question. So of course, there's something that you can do with copula, of course, yes. It's an alternative way of doing things, in a sense.
Yeah, so it would correspond to taking a specific transformation of axis that would reflect the marginals, and then doing the same thing that you are doing, but for those transformations.
Mm-hmm. Yes, but perhaps with copula you're doing it two variables at a time, or you know, pair of variables, and so on and so forth. Here the mutual information takes into account all the, say, covariance structure of, or dependent structure of a process. So that's also a difference with that.
Yeah, so basically it's you don't need covariance of axis, but you do need covariance of H.
Yes, exactly. I'm using that.
Let me maybe
Sure.
also put on in the chat, there's a link to a paper by Mori and Shekeli about how about the representation of multivariate distributions, similar to what also Rustam has posted for copulas.
Okay.
It might be helpful. Anyways, thanks, and sorry for the interruption. I'll mute myself.
Thank you very much. Any contribution is most welcome. Just to finish, can we use ZT for testing unpredictability? I've been exploring this by Monte Carlo simulation experiments. Essentially, what I do is I generate a number of time series of different lengths. And for each series, I determine the most predictable aspect of the time series, and I test whether there is significant serial dependence by using a portmanteau test statistic like Hong's. Think of applying, say, Byung box, whatever, other statistic, but I report only the evidence for Hong test statistic about the serial correlation of the Z. So what happens here, just to cut the story short, I investigate the size by considering several processes according to which XT is IID Gaussian, XT is log normal, XT is student T with 3 degrees of freedom, XT is alpha stable with no asymmetry or with symmetry, and so on and so forth. And the size, you know, size is pretty good, I would say. Here I have the empirical size of Hong test. I consider, along with the Hong test, also a modification of the Hong test with a power transformation proposed by Chen and Dale. So that's the other statistic, which behaves rather well. So my reference value would be this line here. H delta 0.2. 0.2 is the bandwidth of the 2K Hanning kernel that is used for this statistic. So this is for the XT-IID. Nothing changes much if you consider the log normal process. If you increase R, then you have size distortions. You have size distortion increasing with R. That is more overfitting, more evidence, more spurious evidence, more false discovery for a serial dependency in the ZT when there is none. Then I study the power using some well-known processes in the field, the nonlinear MA2 process that I have already considered, the Arch-1-1 process, and the threshold autoregressive process, a bilinear model, and so forth. What happens there is that the power is really high. That's the rejection frequency for the nonlinear MA2 case. Of course, power increases, but also size deterioration are there when R is, so the properties are already very good with R equal to 1, I would say. This is the case of the Gaussian Arch-2 process. The Arch-2 process was, this is actually a typo. It's an Arch-2 process, and that's the process that is considered. I took this example from the literature. So you have this kind of situation. You have a little bit less power for the Arch-1-1 process. And the reason being is that you see here what I'm doing is a truncation of the partial autocorrelation structure. So let me go back to the criterion that I'm using. I truncate the serial partial autocorrelation structure. So effectively, I'm using a 2L autoregressive representation in a sense with some regularization of the partial autocorrelation here. So when you have a substantial moving average component coming in, such as in the Arch-1-1 process, let's look at it again. So here you have say a moving average coefficient, which is 0.94. Very close to the region of non-invertibility, you know, then this test loses some power. Also for the, yes.
Am I right to understand that you could do alternatively the same tests, but based on the original series, non-transformed?
Yes.
And kind of have two tables and see if this transforms raise power.
Very effective. Yes, of course. Yes. That can be done, and it is like you said. Of course, you for the nonlinear MA2 process, you have essentially no power from on the original scale, and so that. But yes, of course, that would be good to show.
Yeah, and also maybe I forgot already. So how do you do inference for tests? And do you need to take into account that there are middle steps where you do estimation of betas, etc.?
Yeah.
How this affects the critical values of the tests?
Very good question. I have to show that this test is consistent and has the usual properties after estimation of the beta. So in my simulation, I just use it as when appropriately standardized, this becomes a standard normal test statistic, and I use that. So yeah, I have no theory for what you ask, Igor, at the moment. So what are the potential side and power distortion due to the estimation of the betas? But should be investigated, of course. Perhaps I'll go to the conclusions. So the method presented here, another way of estimating the mutual information, which is a big concept. They have a less ambitious agenda, which is to estimate that transformation that reveals predictable aspects of the series, right? Only when you see, like in the log normal case, in the nonlinear MA2 case, you're getting very close to getting towards the true, say, mutual information between past and future. So when you discover that there are no further aspects that are predictable from the time series, then you can be confident of that. But otherwise, this is just a device to discover these most predictable aspects. And I think that they can be used for testing the null of unpredictability. The properties of this test are very well comparable to the literature on serial dependence and independence that I referenced, perhaps more powerful, say, and the size distortion are, so in general, they behave well. This is what I mean. The next issue, which is left unexplored, is what Igor was mentioning before. How do we use this for predicting aspects of the original time series? That's something that we need to do still. So thank you very much. This is my conclusion. Thank you for your useful suggestion.
Thank you. Thank you, Tommaso. Any questions for Tommaso? Yeah, so basically you're proposing ways of finding this transformation that is maximizing mutual information between the past and the future, and that is done over the entire range of axes. So R is also part of the inference process. Yeah. So yeah, of course. Yeah, it's a very, very nice pictures the ability to actually break down the dependence into different transformations, right? So that you could think of them as being various moments of the distribution that you can make inference on, right? And that's yeah, because the alternative that I'm thinking about is because clearly H has to be important, because this is what makes dependence, multivariate dependence. Yeah, and so here you basically let the estimation process drive what H is. Yeah, the alternative would be to look at dependence itself, right, based on rank transformation. And I wonder, of course, you're going to lose this ability of showing the different proving tests, like showing the tests that you have. You could have one transformation, the most important dependence driver, right? The second most important. But yeah, but there is an underlying. So if you take all of it, if you have multivariate distribution of x's, there is an underlying true H. Right. Now, by minimizing a linear mutual information of a linear combination of the estimated H's, do you actually recover the true H? I mean, is there consistency?
So the H, in a sense, it's your choice, and you choose the measurable function. So these have nice properties if the original series have nice properties. Sometimes they have better properties like boundedness, right? So these objects are nice just because sometimes they can be bounded. Moments can.
Okay, so H is a given basis.
Yeah, that's given. Really, that's given. So you decide, and then apart from quantile estimation, so you have the uncertainty about the quantiles. That's it, right? Because you replace them by the empirical quantiles of the distribution.
Yeah. So you really don't need to know the true H, so to speak. That generates the dependence with these multivariate H axes, right?
The only thing that you don't know is the location of the H. So the quantile is the location is estimated. So that's
so if you go the alternative way, if you go to that slide where there's the copula representation, right? You could estimate the join of, you could estimate pi by estimating C.
Yes.
Right? and then you could maximize joint information by mutual information by maximizing.
Yes. So what you are suggesting here, Artem, is even more relevant. So now you are actually addressing the estimation of this guy.
Yeah.
Right. I'm turning around. I'm finding an easy way out, which somehow I go to linear combinations and I use as if the process was Gaussian, and then I use partial autocorrelation. That's very convenient, right? But if you want to do,
your point is to be able to show the various aspects of that linear combination.
Yeah. Yes.
Right. So that makes sense. But of course, if you want to think about a generic dependence, right, then restricting H and then making it making mutual information a linear function of H is restrictive, right?
Oh yes, yes, of course. It is restrictive, although you see your basis is fairly general, right? It can account for linearity or, like rank transformations. It can account for non-monotonic function. Of course, it cannot account for, say, something that is periodic or whatever. You could use a Fourier basis, but, my experience with that is rather tragic, I would say, because, you are asking too much, the overfitting then you can get anything. Now, this would be very interesting for me. I'm not much skilled on how to get this. But, for estimating the mutual information, there are several approaches. So here you have to face the curse of the dimensionality. You have a high dimensional, although this is considered two variables at a time, you need to condition for all the intermediate variables. With, you are prone to the curse of dimensionality here, because essentially there is no way out. So it's very interesting, this strategy, right?
So effectively, what you're doing is approximating C, assuming a very strict format for dependence, right?
Yes.
With a specific H's and a linear combination so there's an implied C in your construction of the mutual information. And if we wanted to estimate the C, we would need to, this is the good bit, is that this is bivariate, but there's conditioning on many x's, which means integrating over many x's potentially. But the copula itself is bivariate, and there are very nice approximants for those, right?
Yes, Artem. So I rely on you for suggestion on this literature, and would be very would be nice to go and try to get this guy and to sort of estimate this quantity here, which is the generalization of that. That would be very nice.
I'll send you one link to a paper that does bivariate spline-based approximation of copulas, which may be relevant. And once, but that's done by non-parametric MLE. But in the case of mutual information, there would be also a very similar type of methodology.
You are sending in the chat?
I'll send it in a minute. Yeah.
Okay. Great.
Okay. Let me just see if there's any other questions or any other comments from the audience.
Okay, if I can add also a kind of line of defense.
Yes, please.
There are many kinds of transformations you can think of to measure dependencies. And you can do ranks, and you can do informational stuff, and etc. So, for example, as I see these different transformations, like ranks, they help to robustify to outliers and robustify to some kind of misspecification. While informational criteria, they have some properties. I'm not a specialist, but they have some optimality properties, like measuring distances between distribution is optimal in some way. So I would think that maybe you can do one step further and get this optimal result on information, existing optimal result, and translate it into some optimality of your testing procedure, because you use an object which is already quite good. So if you are doing maybe power calculations, maybe you can translate results for optimality of these informational measures of dependence to the optimality of the tests, something like that. And that would be beautiful theoretical result.
Yes, thank you, Igor. That's I think that the way forward would be to look at and trying to estimate this guy and test about this measure of partial dependence, which is the key ingredient here. No, I'm sure of that. And the reason why I haven't been looking at it is that I concentrated in the second part, and my skills are not so strong here. But yeah, I will read and follow your recommendations on this literature. I think it's a very interesting thing. The literature has been looking at estimates of mutual information based on non-parametric density estimate of multivariate density estimate. For instance, you have Barrett and Samworth. They do work on mostly for testing independence, not in time series. And they use k-nearest neighbor methods for estimating the density. So yeah, it's very interesting literature. Surely there's a lot to be done.
Thanks, Tommaso. Any other questions or comments? No? Well, if there are no more questions, then maybe we can stop the recording and the broadcast, Alex. And perhaps just have a brief chat offline.
Okay. So I thank you for your kind hospitality and for the many suggestions and recommendations. They will be very useful for me. Thank you very much.
Okay. Yeah,
okay.
Great.
So
well, thanks very much, Tommaso. It's great to see you.
It's great to see you. It's fine. You know, when I came back from Oxford, which is the last time we saw each other, I had COVID, right? Already.
You
yes.